All right, it's a great honor and great pleasure to join so many colleagues and friends to honor Professor Yao, someone whom I've known. Well, I first met Yao 37 years ago when I think he first came to Harvard, and then for a period of time, never saw him. He must have been a very busy person at the time. And but I finally came to Harvard again in 1992 for a job interview, and that was that was sort of the beginning of our friendship. He is of course someone all of us admire greatly. But particularly as an old friend of Yao, I've learned a lot from him, both at the mathematical level and also at a personal level. So I'm very happy to be here to join him in this celebration. Okay, so I'm going to talk about some recent joint work with that started with Yao and other collaborators, and then sort of morph into a larger, more interesting program that basically explore a very large new class of mirror symmetry phenomena. In particular, this is it's new in a sense that this is a mirror symmetry for singular Calabi-Yau variety, a subject that has only been very recently started being explored. Okay, so, and I apologize that my transparencies are written rather than the usual LaTeX. Since I've been traveling, my LaTeX on my computers is sort of acting weird. So rather than spending hours to fix it and ended up not being able to fix it and write my transparency, I decided to just do a handwriting on my iPad. Okay, so let me start with a cartoon picture. So I like to call this the homological mirror symmetry opera. So it's kind of like, think of it as a very complicated play in which there are lots of plots and characters. So this picture below it is roughly sketching what I'm about to talk about. But I will only have time to focus on some pieces of it. All right, so what is it? So I'm going to start from some combinatorial data. So let's see. This is the laser. Okay. The combinatorial data is a pair of integral polytopes. So these are convex hull of integral points in Zn. And they are dual in some sense, and I'll make precise what it means for this pair of polytopes to be dual. And not only that, each one of these members of this pair can be decomposed into Minkowski sum of some smaller polytopes, okay? Delta K and nabla K. And from this pair of data, there are supposedly a pair of Calabi-Yau variety, which I call Y and Y check, okay, constructed in some canonical way, which I'll describe. And from those, you're supposed to get a pair of categories. I would generically call it an A category and a B category. Now, depending on the setting, this A category could manifest itself in some geometric way, and the B category in some completely different way. But nevertheless, the two categories are supposed to be isomorphic. Okay, there's supposed to be some functor that relates the two. And there's in some favorable situation, you're supposed to be able to show that the two categories are in fact isomorphic under that functor. All right, moving on, from the category, there's supposed to be some construction, so this box arrow, that give rise to a couple of local systems. So one is called a period sheaf, the other is called a B period sheaf. The term A and B comes from physics, and I won't go into the history of that, but suffice to say that this sequence of construction and this sequence of construction is supposed to recover another direct construction from the Calabi-Yau variety to the period sheaf. So this is some kind of a commutative diagram at the categorical level. So the bottom line of my talk would be the statement that these two local systems, this A period sheaf constructed from this polytope and the B period sheaf constructed by this dual polytope are actually supposed to be isomorphic in some specific way. Okay, I hope to at least get to this point, and if not, at least get to half of this. Okay. All right, so this is based on my joint work with TJ Lee and Mauricio Romo. One is in Taiwan, the other is in Tsinghua. And also based on my earlier joint work with Shinobu Hosono, Hiromichi Takagi, and ST Yao. All right, so let me start with classical mirror symmetry. Now, I have to warn you that anything in mirror symmetry over 20 years is considered classical. Okay, so the term classical means different thing in mirror symmetry. All right, so let me start with a, oops, sorry. I want to start with a complete toric variety, call it Xn of dimension n. And I will choose a particular algebraic torus in this way. And identify the dense torus in my toric variety with this standard torus. Okay? Now, the effect of that is that you can then now express every sections of every holomorphic line bundle on X in some canonical way as a Laurent polynomial. So essentially, this choice induces a linear map from, in fact, a linear injection from the space of holomorphic section of the line bundle L into the ring of Laurent polynomial in n variable. Okay, and this map is depend canonically on this choice. Okay, so next I want to introduce the notion of a reflexive polytope. So delta is a reflexive polytope. There are about six or seven different definitions, but I'm going to give you the simplest combinatorial definition. So a reflexive polytope is an integral polytope. So it's a convex half of finitely many integral points in Zn, such that it contains the origin as an interior point and the only interior point, the only interior integral point in the polytope. So this would be the simplest example. Okay, so a convex half of these 3 points given by standard basis E1 and E2, and minus E1 and minus E2. And you can draw a picture to convince yourself that the origin is the only interior integral point. And this is another example, okay, where you just take the 4 corners of a square, distance 1, a square root 2 from the origin. Okay, now from every such polytope, you can construct something called the normal fan, which I denote by sigma delta. The normal fan, I won't get into the precise definition, but you can sort of think of it pictorially. What you do is, so you want to construct a collection of integral polyhedral cones, in fact, convex polyhedral cone. And the way you do it is that you go to every corner of your polytope, and you take the normal fan. So for example, if I take this polytope, the normal fan will be obtained by the normal cone at this vertex will be obtained by taking a 90-degree line to this edge, and then a 90-degree line to this edge, and you would get a cone that looks like that. Okay, and you do the similar thing on here, and then you shift that cone to the origin. That way, you get three separate polyhedra convex cone in Z2. And those three cones together with their faces form from this fan sigma delta. We call the normal fan of the polytope. Okay, and you can do the same with this one as well. And if you do it with this one, it's easy to see that the fan that you get would be just the 4 quadrant, the R2 split into the 4 quadrant. Okay. So a little bit of elementary toric gymnastics. So for every fan, you can obtain a toric variety. In fact, when the fan is complete, in the sense that if it fill up Rn, then the toric variety you get from it will be a complete toric variety. So this would be denoted by P nabla for simplicity. Okay. So from this data, you can get one more set of finite set of data. And that is because this fan contains not just the two-dimensional, in this example, not just the n-dimensional cone, but they are also their faces. So they are lower dimensional cone. What you can do is you can put all the one-dimensional cone into a set. This is called, I denote it by sigma of 1. So this is a set of all one-dimensional cone in the fan. All right, so this is some finite set. And again, some toric gymnastic tells us that every such one cone corresponds to the one cone's parameterized T-invariant toric divisor, T being the torus. So these are divisors obtained by taking codimension 1 orbit of the torus and then take its algebraic closure. What you get is a divisor in the complete toric variety. I denote this by di. If I labels a one cone, I call the toric divisor di. Okay, next I introduce a definition, an important definition, the notion of a Neff partition. So I still start with my polytope delta, and if a decomposition of this finite set into subsets is called a Neff partition, if the following is true. Now recall that every element, every one cone give me a divisor. I take the sum of this divisor corresponding to each of these subsets. Divisor correspond to line bundle, and if each of these line bundle is a Neff divisor, Neff stands for numerically effective. So if this is a numerically effective divisor for each of these subset, we call this decomposition a Neff partition. Okay. And as an immediate consequence, you can show that the anti-canonical class of our toric variety P delta is the sum of this Neff divisor. So that's where the term comes from. You decompose the anti-canonical class into a sum of Neff divisor. Okay. Now, it turns out that also can be recast into a combinatorial statement as follows. So if you take, remember that EK is a line bundle because it's a divisor. So as a line bundle, you can consider its holomorphic sections. And I just mentioned that every holomorphic section can be thought of as a Laurent polynomial. Well, it turns out that the space of section is spanned by not just Laurent polynomial, but actually Laurent monomial. And each Laurent monomial is specified by an exponent because it's just t to a power of a vector. And you put the vector is an integral vector in Zn. So you can take the set of all such monomial and form a polytope. That's called the section polytope of the line bundle Ek. All right. So every such line bundle gives rise to a section polytope, an integral polytope called a section polytope. And as a corollary of this Neff partition, you can show that the original polytope you started with is actually the Minkowski sum of the section polytope appearing in the Neff partition. Okay? So it's a very simple way to translate between combinatorial data and geometric data of with regard to the anti-canonical class. All right. Are there any questions before I move on? Okay, no question about notation. Okay. Next, you can construct now a dual object from this original data. Okay, and the way you do so is the following. Remember, I decompose my one cone into a bunch of subsets I call IK. The IK can be thought of as a set of vector because every one cone has a unique integral vector that spans it, that generates it, right? You think of it as an, you look at all because it's a rational cone, it's generated by an integral vector. There's a shortest integral vector, non-zero intervector in that Rak-Kyeong. So you can take those vector and think of ik as a set of all such integral vectors. So you have a set of integral vector ik, and you adjoin to it the origin, and then you take the convex half. So what you get is a polytope with one point as vertex at the origin. Okay. Okay. So since I have R such subsets, I get R such polytopes. I can take their Minkowski sum and form a new polytope called nabla. Okay. Okay. So and this is the key result going back to Borisov. So Borisov showed that this construction gives rise to yet another reflexive polytope, okay, which I denote by nabla here. Moreover, this decomposition into these this smaller polytope is actually coming from a net partition. Okay, so in other words, this purely combinatorial construction actually has a geometric origin. Okay, so and he called this the dual net partition of this one, the one that you started with. Okay, so for every net partition of a reflexive polytope, you get for free another one called the dual net partition of a different reflexive polytope. Okay. All right. Now I'm going to make one further assumption about this data. So I start from delta, I get a nabla. So there are two questions you can ask. Suppose you start from nabla, would you recover delta in the sort of in a completely parallel way? The answer is yes. Okay. So nabla and so this relationship is actually involutive. From delta, you get nabla, and you can come back. The second question is, well, if you take nabla and delta, you form the toric variety using the normal fan construction I alluded to. You get two toric variety. And the two toric variety, this pair of toric variety is typically singular. So you can ask, how can we resolve it? And what is the best way to resolve it? It turns out that the answer to that question is complicated. It depends on the dimension you're in. Okay, so what the assumptions I'm about to make sort of make that complication go away, sort of make the whole construction uniform and just forget about the complication. The assumption I'm going to make is the following. I have to introduce a notion called MPCP type. So it stands for maximal projective Kreplin partial resolution. Okay, MPCP. I dropped the R. So this notion was introduced by Batirev back in the early 90s. Again, there are 6 or 7 different ways to characterize this notion, but I'm going to give you the simplest combinatorial definition. What that means is that this polytope admits a center unimodular triangulation. Remember, this polytope contains the origin as a unique integral point, interior integral point. So a center triangulation means that every subpolyhedron in your triangulation, in the standard topological sense, contain the origin as one of the vertex. That's what it means to be center. I'm going to give you a couple of simple pictures to illustrate this notion. All right. So it turns out that making this assumption has many useful consequences that avoid many complications. Okay, so I'm going to, from now on, assume that this pair of polytope satisfy this MPCP type condition. As I said, this condition actually depends on dimension. So for example, up to dimension 3, you can show that this is a vacuous condition. Every reflexive polytope is MPCP if it is dimension 3 or less. But in dimension 4, in fact, quite typically, the MPCP is actually the minority. Okay, most reflexive polytopes are actually not MPCP. There are only finitely many in each dimension up to linear transformation. But if you look at the list, most of them would not be. Okay, now so an immediate geometric consequence of this condition is that each one of this, so take P delta this complete toric variety, we'll have what we call an MPCP resolution. So what you do is that you subdivide the dual polytope by using this triangulation that you have, this unimodular triangulation. So each of this polyhedron correspond to a cone in the dual fan. And so by the unimodularity property, it ensures that what you get is a new toric variety that's actually smooth, and it give you a canonical, once you fix the triangulation, it gives you a canonical resolution of this singular toric variety. Yeah. Okay. So the MPCP resolution is actually an actual resolution, not just a partial resolution. That's sort of the point of the MPCP condition. Okay, so under this assumption, I get a pair of smooth toric variety, which I denote by X and X check. They correspond to this pair of reflexive polytopes, delta and nabla. Okay, now from this data, you can go one step further, and this is where mirror symmetry comes in. So let's take X. X determine a Calabi-Yau complete intersection in the following way, provided that R is less than N. So R is the number of subsets in your net partition, right? You subdivide the one cone into R subsets. So that means you have R net line bundle, and then you take the sections of each one of these R line bundle. Let's call it SK, and then you pick a generic section, and then you take their zero set. What you get is a codimension R subvariety of X of this smooth toric variety, and the usual adjunction formula tells you that Y will be a Calabi-Yau variety, and for generic S1 to SR, this will be Y itself is also smooth. And you can do the same with the dual net partition. Since the story is completely parallel, you get another Calabi-Yau manifold for generic section, SY check to SR check. And so you get a pair of, from a single data delta, you get under the assumption of MPCP, you get a pair of Calabi-Yau manifold, depending on the choice of these generic sections. So you get two family of Calabi-Yau manifold. So here's a numerical example. So if I start with this polytope, I call delta. So this contains the origin. These are the three faces of my polytope. Okay. So as I said before, because this is the dimension 2, it's automatically MPCP, and you can see it easily, right? You can just take these sub one cone, take two adjacent point, and join to it the origin, and you get yourself a triangle. And then you can fill up the delta with a bunch of smaller triangles. Yeah, that gives you a triangulation. Now from here, you can break it up into a Minkowski sum of three subpolytopes: delta 1, delta 2, and delta 3. And you can easily see from the picture that the Minkowski sum of these three guys give you the recover delta. And you can from this you can calculate the section polytope, and you can take the convex hull as I illustrated before, and you get these three edges as the convex hull. And taking the Minkowski sum of this, you get this new reflexive polytope. So from delta and from this choice of net partition, you get this new dual net partition of this new reflexive polytope. So this would be an example of what I said earlier. Okay. All right. So this is the old story. So Battier and Borisov show that this pair of Calabi-Yau manifold forms a pair of mirror manifold in some sense. So it satisfies a bunch of tests. The first the first standard test is a topological test. You look at the Hodge diamond of Y and Y check, and they show that the Hodge diamonds are mirror to each other with respect to a reflection along a certain diagonal. And there's also other a more refined topological test called the ACCC ring test. So from this pair of toric variety, you can compute a couple of topological invariants called the AC ring and the CC ring. And you see that they're actually isomorphic to each other under a certain suitable isomorphism depending on the initial data. And the even more refined test, which actually makes mirror symmetry famous to mathematicians, is the so-called quantum Yukawa coupling test. That first done by Candelas and his group, the famous paper of 1991. And this was generalized to arbitrary pair of reflexive polytope in the setup of Batyr Borisov by Hosono, myself, and Yao in the early 90s. There's, of course, the next level of quantum tests that goes back to Brzezinski, Ciccadi, Uguri, and Rafa using the theory of topological string. Okay, so now the question is, well, what happened if you take sort of try to do something stupid instead of complete intersections of R sections, you allow R to be big to exceed the dimension. Of course, naively, you're going to get an empty set because complete intersections of negative codimension is obviously empty. So the new result, it turns out you can think of it as a reinterpretation of empty set. Okay, so that's where the term fractional complete intersection come from, which is something I want to explain next. Okay, so consider instead of a subvariety, you consider twofold cover. Okay, so I still have my X check under my assumption. So X check is my MPCP resolution of P nabla, and I look at the 2-to-1 branch cover, branch along a divisor given by twice the anti-canonical class of the base. Okay. So in general, Y check would be a Calabi-Yau variety. It's smooth if and only if the branch locus is smooth. The case that we'll be interested in is the case when the branch locus is actually not smooth, which is something I think Chen Longyu was talking about in his talk earlier, where you can specialize this where the base is Pn. All right, so I would call the 2-to-1 cover a fractional complete intersection, or FCI for short, if the branch locus is of this special form. So what it is that it's given by a set theoretic union of divisor given as presented as a product of two sections. Okay, S1K and S2K, where S1K and S2K are specified by my Neff partition. Notice that this definition does not restrict the value of R. So my Neff partition could be as fine as I want to make it. Okay. Here. I'm going too fast. All right. So I make two additional assumptions about this branch locus. The first section is required to be represented by the Laurent polynomial 1. It turns out that 1 is always in the space of section. So I choose specifically the first section to be that special section 1. And the second section is allowed to vary. Okay. So the only variation is in the second factor. The first factor of every component is given by 1. I also require that this branch locus is a simple normal crossing. So this divisor D. Okay. So this is my definition of what we call B period. So for every such 2-to-1 cover, I write down this holomorphic N form on Y check, and I write it down in the coordinate of the torus downstairs, and pull it up to the twofold cover on Y check. And this turns out to be exactly the top form on my Calabi-Yau variety Y check. Notice that by definition, an FCI is singular, right? The singularity is exactly where these divisors meet. Okay. All right, so since I'm picking a certain canonical top form of y check and integrate over a rational, this is a typo. This is not 0. This is supposed to be n. So I'm integrating over an n cycle of an n form. What I get is a locally defined holomorphic function that depends on the section S21 to S2R. Okay, this is called a B period. So this set of B period form a local system of analytic functions. So they transform into each other under monodromy. And notice that this very peculiar form where you're taking 1 over a bunch of sections, essentially long polynomial to a power 1/2, okay, to a power 1/2. And for those of you who've studied complete intersections and their period, you will notice that this is very analogous to the case of complete intersection, the classical case, where R is strictly less than or equal to n. Where if you write down the B period, you would get this form, where the exponent in the denominator is actually 1 rather than 1/2. And that's where the term fractional comes from. So it formally looks like the period of a complete intersections, except that the exponent is 1/2 rather than the integer 1. Moreover, R here is unrestricted rather than it's restricted here, R being less than or equal to n. Here, R is arbitrary. Okay, so this is where the term fractional complete intersection come from. All right, so this is the first main result we proved recently. Okay, so the families of FCI, Y check and Y. So you get a pair because you get a pair of reflexive. You start from a reflexive polytope, you get a dual polytope. So the claim is that this pair of a Calabi-Yau variety satisfy the topological mirror test. So you can calculate their Hodge numbers, sort of the orbifold Hodge number, and you can show that at least up to dimension 4, the Hodge diamond are mirror to each other. Yeah, we expect that above n equals 4, this still holds true, but somehow the combinatorial proof we have breaks down. There's not enough sort of tool to settle the beyond this bound. But you can do a partial test. Instead of looking at the full Hodge diamond, you add them up and calculate the topological Euler characteristic, and you get this expected mirror relation between one mirror Calabi-Yau and its mirror partner. Okay, it's given by -1 to a power n. This is sort of the famous Euler characteristic test. One can also perform the ACCC ring test, and one can show that, one can prove that as a theorem, that it also passed that topological test. Let me make a couple of remarks, and since I'm out of time, I'm going to finish with this remark. So under some technical assumption, you can go on to test the quantum Yukawa coupling problem, and you can show that because the variety that the Calabi-Yau, the mirror Calabi-Yau we're dealing with is singular, they have orbifold singularity. You need a slightly more subtle way to talk about Gromov-Witten invariant, and the theory has been developed by Chen, Ruan, and other people. So if you use that, apply that theory, you can show that the B period of one of the mirror partner, Y check, correctly predicts the orbifold Gromov-Witten invariant of Y, the mirror partner, at least in genus 0. And of course, you can say, well, what about higher genus? Well, that would be our next paper, which is still being written. Okay, so this, but we expect that even the BCOV test, this pair of new mirror also pass the test. Okay, since my time is up, thank you and happy birthday to Yao.